All right, so we're going to talk about basic differentiation formulas. So here, we're going to let C be a constant. Be a constant. I don't know if I said that. So let's let C be a constant. So if C is a constant, the derivative of a constant is 0, right? So we always know what this is. And so here we have d dx. D dx is another way, remember, d dy dx is just a way of saying this. And so when you see d dx, that means take the derivative, right? Or perform the prime, right? That looks like a y. And so d dx is to take the derivative. It means to perform this function. So here means if I took the derivative of a constant, I'm going to get 0. If I took the derivative of just the function x, I get 1. Here, if I take a derivative of any x to any power, I'm going to get n. So whatever that power is, to n minus 1. And let's just do a quick example real quick. So here, x to the 4th, if I took d dx of it, this is equal to 4x, and then n minus 1 would be 3. So 4x cubed. And here, this is the same thing of saying f of x is equal to x to the 4th. Then f prime of x is equal to 4x to the 3rd. So what this means right here is to take a derivative. So take a derivative of whatever on the inside. So if I took the derivative of this, it's the same thing as, so say the same thing as saying f of x is this function, its derivative is this function. Well, that'd be the same thing as saying the derivative of x to the 4th is 4x to the 3rd. Okay. And we'll work through all these. Here, the constant multiple rule means if I have a constant, I can just pull it out and take the derivative. So the sum rule, if I'm taking the derivative of two functions, and if it's one function plus another, I can just take derivative of one function plus the derivative of the other function. Same thing for difference. I can take a derivative of one function minus the derivative of the other function. And here's some other things real quick. So here we have e to the x. So e to the x, its derivative is itself, right? And that's really kind of a gives the rise to a horrible math joke. And so here, its derivative itself. And here, if I take the derivative of sine, I get cosine. And if I take the derivative of cosine, I'll get minus sine. Okay. And from these rules, right, you can take a derivative of many, 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 many things. Now, the proof of these is given in your textbook. If you're interested in foreign foot, you can look over them there, or you can do the online resources. Or they basically follow what we learned in 2.1, 2.2. They just do it generically, I guess. But I'm not going to test you on these proofs. And so unless you really want to learn the proofs, don't worry about it, right? I guess it's terrible to say. So let's use a graphical or verbal explanation of why these two are that. So let's just do it graphically. So let's just say I have some C here. Notice, what's the slope of this line for, because this is f of x is equal to some constant C, right? And or if you wanted to, you could say this is 2 and 2, right? f of x is equal to 2. Well, the slope of this line everywhere is 0, right? It's a flat line, right? The rate of change here is 0. No matter what x I put in, I'm getting back the same. So here, the slope is 0. Now let's look at x. Here, it's just the slope of, if I horribly miss, see if I can do this. A little better. The slope here is always 1, right? Here we have f of x equal to x. This is always 1. And because here it goes over 1 and up 1, over 1 and up 1, over 1 and up 1. So it's a straight line, so it has a constant rate of change of 1. And we use these to kind of help us to work through some things. All right, so I'll let you draw that real quick, and we'll do the next page. All right, let's go ahead and export this, because I know I'm going to get crunchy. All right. So let's look at some of these. Let's use these rules. I probably needed my rules up. Yeah, that's fine. I'll just write them out. All right, so as previously shown that x squared becomes 2x and x cubed becomes 3x. So we're going to, from using the definition, now we're going to verify these using the formula rules. So we're just going to use the formula rules and then we're going to sketch, and then I'm going to sketch the derivative of the function below. Okay. All right, so let's just do this real quick. So here, using we're now going to use this thing. So here we're going to find d of, dx over 2. And remember, this means nothing more than take a derivative. So here, I'm going to take whatever power I have here, drop it down, so it'll be 2, and then I'll have x, and then I'm going to take 1 minus that power, so 2 minus 1 is 1, which is just equal to 2x. So here, we just go ahead and draw this in. And so here, let me draw, I guess blue's fine. Draw a point here, draw a point here. So So from here to here. All right, so we draw on this line. Okay. So notice here, the derivative at this point is 0, and we have it to be 0. Notice here, my rate of change here, my instantaneous rate of change here is about 2. And here at 2, it's about 4. And then it just goes up. So here, we can draw in the derivative. Here, we have x cubed. We just used our formula, so d dx of x cubed. So using this formula here, we just drop down the 3 and take 3 minus 1, which is 2. So here we get this. And if we were going to graph that real quick, this will be 3 times x squared, so it would be 1. The next spot would be over 1 and up 3. The next one would be over 1 and up 12, so like way off the graph. So roughly like this. Now, does that make sense to what we see here? Yeah. Is this graph ever decreasing? No, the rate of change is always positive, right? And so it's really strong, and then it slows down as it does, as it slows down. So here, it's positive, positive, positive rate of change, slows down, becomes negative, and then more positive rate of change. And so here, that represents that. Okay. All right, so we can use this formula here to solve even more complicated things, right? So here we can take square root of x. So d of dx of the square root of x is the same thing as taking the derivative. Well, the square root of x is the same thing as x to the 1/2 power. Well, if I do that, I just take whatever's here, drop it down, so I get a 1/2. And then I get x of 1 minus a 1/2 minus 1, which would be minus a 1/2, right? But if I rewrote that, that gives me 1 over 2 over the square root of x. Because here, a 1/2, and then here this would be the square root of x, but on the bottom. And here, I went ahead and graphed it for you since this is really kind of complicated. Okay. And so notice here, I have positive rate of change always. And so it's right here, it comes up really sharply and then it levels off, right? And so my rate of change levels off here. Okay. Now we can do the same thing here for 1 over x. And so here we have d dx. In order to do what we want to do, is we convert it into a form like this. Well, can we do that? Sure. This is the same thing as x to the minus 1 power. So this and this are the same. So once I take this, so I take this, then drop that down, so I get minus 1. And then here, negative 1 minus 1 will give me minus 2, so this will be x to the minus 2 power. Or if I rewrote this, I'll have 1 over minus 1 over x squared. And so here we go. And so here we have the graph of our function, 1 over x. But notice this is always decreasing, right? This function is always decreasing. This function is always decreasing. And so if we look here at its derivative, it's always decreasing, and the rate of its decreasing increases greatly as I get to 0. And then here, it's mildly decreasing here. And then as I get back, it slow levels off. Okay. And so this is nice to see the function and its derivative map together. Some of your homework requires you to, given a function, show its derivative, or given its derivative, show its function. So you just click on the right graph. Okay. In figure 3, you move the x squared to number because the exponent is negative. Yes. So here, if I was going to do this, I can do one more step. Let me do one more step. Let's see if I can help you guys. So here I can take x to the minus. I can split it up this way. And so this is square root of x, and then this means put it on the bottom. Yes. All right. So for this formula right here, this solves a lot of your issues because any polynomial you can pull out. You can just drop down your exponent and then -1 from it, drop down. And so this works for anyone. Anything that has this form or doesn't quite have that form, but you can put into this form. And so it just ends up being a lot faster way of doing it. Okay, so let me let you write that down, and then I will switch pages. And since I'm out of water, I'll have to go get water between classes. All right, so let's go ahead and export this. PNG. Oh, save. All right. Don't save here. All right. So let's use this for an application. All right, so a rock is launched into air, and this is why we learned calculus. Calculus is independent, so Newton can do his physics. So the why it was invented. A guy named Leibniz. No, I'm saying it wrong. Also invented calculus at the same time as Newton, but Newton was Sir Isaac Newton was in charge of the Royal College of Arts, and so he put his name on it. So it's just how it works. Anyway, so use the derivative rules to calculate S and S prime. So here we're given a position of a falling rock looks something like this, right? And this is usually a rock. You launch a rock in the air, it's going to go up and up and up until it finally starts, the gravity overwinds and it starts going down. And so it looks something like this, right? If I graphed it. So here, if we're given S of t, and I want to find, so S of t is 40, t minus 16t squared. So I want to find d dx of S of t, which is equal to S prime of t, right? Well, here, let's do this. So let's do this one small step at a time. And so here I'm going to take 40. So 40 I can pull out, right? And then I can take d dx of t. So here, hold on, let me write this the other way. If you have it written this way, it's not wrong at all. It's just I want to make it clear what I'm doing. So S prime of t is equal to d dx of S of t. And so here I'm going to plug that in. So here I can pull out the 40. Actually, no, let me do the first one. If you have this step, don't worry about it. S of t. So let me do this. So I have d dx. Let me do this one very slowly the very first time. Plus 16 t squared. Then by my addition rule, I can say this is d dx of 40t plus d dx. But is it d dx in this case? No, my independent variable here is t. So I'm sorry. I'm sorry about this. Use a t. So d dt means take the derivative with respect to this variable. And so here we have a variable of t because we're using t time, not x in this case. All right, so here, take the derivative means to take the derivative for all of this. So our first rule allows us to split it this way. So here we're using that power rule, or sum rule. So here we're using the sum rule. So here I can split it up. Then what can I do? I can pull out the constants, right? So I can have 40 dt of t, and then I can have so pull out the minus 16 of dt of t squared. And then I can use the power rule here to evaluate this. So here I'll have 40. I pull out the power here. So technically this has a 1. So if oh, wait a second, this is just the derivative of this. So this ends up being 1, right? Remember from my rules? Yes. My negative sign sucks. So let me make my negative sign not be awful. There we go. Okay. So remember, if we have dx, dx of x, it was 1. Here's the same thing for ddt. This is just 1. Minus 16 here. I'll pull the 2 down, so this becomes 2. And 2 minus 1 becomes 1, so t. And so this is just equal to 40 minus 32 t. Okay. Then, so this is equal to my s prime of t. So my s double prime of t is equal to d dt of s of t, right? Which equals d dt of 40 minus 32t. And here, we'll go ahead and just do it all at once. So a derivative of a constant is 0. A derivative of, here we can pull out the 32, so it's be minus 32. And then the derivative of t with respect to t is just 1, so this is just 1. And so this ends up just being minus 32. And that is our s double prime t. Okay. And so here we've taken the first derivative, which gives us this. And then from there, we took the derivative of that function again. So here we're taking the derivative of this function. This gave us minus 32. And so let's go ahead and find what s of 1 is. So s of 1, s prime of 1. So here, if I plug 1 into here, I'm going to get 40 minus 32, which is equal to 8. And so that's what s prime of 1 is. And what does that mean? What does that mean? That is the velocity at t equal to 1. I assume that means seconds, but since this doesn't really, so s in feet and t in seconds. So the velocity at t equals 1 is 8 feet per second, right? So that's what the velocity is. Let's find s double prime of 1. S double prime of 1 is going to be minus 32. And that's the acceleration. Acceleration at time equals 1, and that's minus 32 feet per second. And cents per second squared. And so here we have our velocity, here we have acceleration. Our acceleration is constant. Why? Because gravity is constant, right? Gravity is pulled down at a constant rate. So it's always pulling at a constant rate. So that's what those mean. And you'll have a question like that. Is acceleration always s double prime? Yes. If position, let's see if I can, let me just do a little hierarchy. Yeah, position. If you take the derivative of position is velocity, right? Velocity. The derivative of velocity is acceleration. And the derivative of acceleration are called jerks. I don't know if they're still called that. That's what they were when I called it. When I went through physics, we call them jerks. And because change, so if you have a constant smooth change, or if acceleration is constant and smooth, right, you can feel the pressure, but it's not really that. But say you're driving a car real fast, right? And then so you're accelerating, and then all of a sudden you slam on the brakes, right? So you're turning your acceleration from positive, or in that case, or even if you're just going at a constant speed where your acceleration is 0, and all of a sudden it becomes quite negative, right? Because you've added negative acceleration because you're blocking the tires, right? And so that change is called jerks because you know it feels like that's where it comes from, because it's jerking you either forward or back or something. So that's where it comes from. So this derivative gives this derivative gives this derivative gives this, and eventually we're going to do the opposite. If I integrate this, I can integrate this. And so you can go back and forth. And so this is why calculus was invented, literally to do these problems. We'll start the next section. All right, so here, definition, E is the number. So E is defined to be this, right? Or E to the H. So here, if we take E to the H, is the number such that there's other ways. This is how I was defined. This is how I learned to define E. I take the limit as n goes to infinity of this, and then it produces E. You can also just solve for E given what limit will cause this. Either case, why is my phone not on silent? So in either case, we just care what the derivative is. And the derivative of E to any number is just itself. Okay. And so this one has a really nice property. So E to the X is just E to the X. So it makes it quite simple. So here we're going to calculate. Let's go ahead and calculate one with using E to the X. And then I'll add just 2 more problems I wanted to show you before we moved on to the next section. So here, given y, so if I want to find dy dx of the, or dt, I guess in this case dt of this, so I'd have 7 d dt of e to the t plus d dt of 5. So if I just move this in, I can pull out the 7. Well, this is defined just to be 7 times, well, this is just itself, so it'd be e to the t, and since this is a constant, a derivative of any constant is 0. So this is just 7e to the t is equal to dy. So here, when we take the derivative, we just literally just don't change anything. So literally what happens here. Now the plus 5, well, the 5 is a constant, so we get rid of that. So here, the answer to that one. There was one thing that I was supposed to mention really quick on the 2.1, 2.2 notes. I asked where is it differential, but I never answered. I never truly answered the question. It's differential everywhere but 0. So I just forgot to answer that. So here, if I want to do this, if I want to find this derivative, what I need to do is the first thing I want to do is actually just distribute. So here I'm going to distribute the 1 over square root, or the square root of 3 minus 1 over. And so the first thing I'm going to do is just distribute this here and here. Okay. The second thing I'll do, even before I take its derivative, so here I want to find g of x. So this is still g of x. But here, this is g of x over x cubed to the half minus 1 over x cubed to a half. And if I simplify this, so this is 3 halves, but it's negative 3 halves if I move it up top. So this would be x times minus 3 halves. And we'll just write x to the first power minus x to the minus 3 halves power. And then here, if I put this together, I'll have this equal to x to the half, minus half power minus x to the minus 3 halves power. So here, I still haven't taken its derivative, but all I've done is I've distribute this and just done some of my power rules in order to get it to look like this. Anyone confused how I got to this point? I haven't taken a derivative yet. I've just been doing manipulation on g of x. Everyone see how I got to this point? I just distributed the square root of x square root of 3, redefined it this way. I mean, technically, I guess it would have been faster just to say 1 over 3 halves is equal to 1 over, and then you could have skipped this step. Yeah, so I'm just switching. I'm saying this is equal to this, minus 3 halves power. And then I'm just distributing it across. And then I simplify to get x to the half, negative half, and x to this. Then, when I take its derivative, so here we'll find g prime of x. If I take this derivative, this comes down, so it'll be 1 minus 2, and this will be x, and then I minus 1 from this. Remember our rules. Let me see if I can open up the rules real quick. Where the rules go? Yeah, so remember our rules here. So our power rule is we take whatever power we have here, we drop it up front, and then we take whatever power we have and we minus 1 from it. So here, our power is a half, so we put that up front, and then 1 minus a half would be minus 3 halves, right? Then here, I have this power, and I'm going to drop that up front, so minus 3 halves, x to the 3 halves, and then x minus 1 would be x to the minus 5 halves. Okay. And then if we just simplify that a little bit, here, it just becomes minus 1 over x cubed, like we had before, and then this becomes plus 3 halves. Oops, I forgot my 2 here. And then this would be 3 over x to the 5th square root. And so here, that'd be our answer. Okay, if you leave it like this, unlike the written part of the exam when I give it to you, not next week but the week after, I'll be fine. Your exam, just real quick on this, will be half on WebAssign, and you'll get 2 tries. And then the other half will be you're going to write out by hand and you submit it to me, and I'll actually grade it by hand. Okay, so it'll be about half and half. Depends on what I'm asking. All right, so here, so given a derivative of a function, we can take, yeah, it's x to the 5th, sorry. Almost. There. Does it have to be on? It's fine. It's exactly how you turn in your notes. Exactly how you turn in your notes. I'll fill it out and just give it back to me in that order, right? Okay, so all right, so now let's do something here. So here, remember we can take a derivative of multiple derivatives of a function. On the you can put it in parentheses if it's cleaner that way, so yes. Okay, so here, let's take a whole, you have one there without a, oh, here, this parentheses, thank you. I forgot to pull that out within parentheses. Thank you. Because this negative becomes positive. All right, so let's look at the first, so our first derivative of, so let's look at our derivatives here. So let's look what I gave you on our little cheat sheet. I'll go back to my cheat sheet real quick. So here's our little cheat sheet that we've already done. So sine becomes cosine and cosine becomes minus sine. And so here we're going to find the first 5 derivatives of cosine. And so here, so cosine becomes minus sine of x. And if I took this derivative, so my second derivative here, this becomes, well, I keep the negative 1, right? And then here, I take derivative of sine. Well, sine just becomes cosine. So we're just going to leave this as minus cosine of x. I take the next derivative, and here we just keep putting hash marks. And so once we do this, cosine becomes minus sine, so this just becomes sine of x. So the minus and the minus cancel out, so I just get sine of x. And then here, hold on, let me make sure I do this correctly. All right, so once your derivatives get large, right, you're going to start using Roman numerals. So our fourth derivative will have a Roman numeral here in parentheses. Doesn't mean take the fourth function, it means take the fourth derivative, or the fourth power of it. And then here, this becomes cosine of x. And then here, the fifth derivative is equal to, again, minus sine of x. Okay. And so here, notice here that cosine of x kind of goes into a cycle. And so every 4 times you take a derivative, you get back what you had before. Okay. So I think your book has some of the questions like this. It's like, if you take cosine, what's its, I'm positive your book uses proper notation for that real quick. Hold on, let me look it up in the book. Oh, Booko. Thank you, book. Oh, it doesn't. Oh, it doesn't use Roman numerals. It just puts it in parentheses. Your book doesn't use Roman numerals. Your book's going to do this. That's fine, as long as you know what your book's notation is. Often I see the Roman numerals to make it clear what you're doing, because the Roman numerals means derivatives. This means powers, because you can take powers of function. But since we never take powers of function, this is perfectly fine. And your book was going to ask you, like really fun questions, like what's the 24th derivative of cosine? Well, every time you do 4 derivatives, you get back to where you're at. So 24 divided by 4. Hold on, let me not do square root. Let me write that correctly. So if I took 24 and divided it by 4, I get here 6 remainder 0. And so it just looks like cosine, right? So this is cosine of x. I forgot my x here. And let's just say if I wanted to find the 27th, and so here I just take 27 divided by 4. Here I get still 6, but I get remainder 3. So I'm just going to take cosine. I'm going to do 1, 2, and 3. And so here I get sine of x. Okay. And so here you can actually find an obscene amount of sine or cosine just because they go in this order. Will we ever use tan? Yes, I'll explain how to do that in the next section. Okay. I'll explain how we get to tangent and cotangent, all that other stuff. All right, so wait. Yeah, so the fourth derivative is just cosine of x. There should be an x on there, yeah. Okay. I've always seen it as Roman numerals. Your book's just going to use parentheses if we do that. So use the remainder to figure it out for obscenely large values. So whatever the remainder is. So if the remainder is 0, it's this one. If it's remainder 1, 2, and 3, and then since you're dividing by 4, you won't have the remainder of 4. It'll be 0, right? And so it's 0, 1, 2, and 3. Okay. And so anything that is its own derivative is any function that eventually becomes back to itself for its own derivative, you can do this sort of trick. It's kind of like when you did powers of I. If you have I, so the first power is I squared is -1, I cubed is minus I to the fourth was 1, and then I to the fifth was I, and how it went round robin, you found like really large values of I. So its remainder is 0. Yeah, so since its remainder is 0, it looks like the original function. Because look, here if I take 4 divided by 4 is 1, remainder 0, and that looks like the original function. Okay? And so 24, we'll go through 1, 2, 3. So 24 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and end up here. That was going to be with how all the derivatives look like. All right, so